Hi everyone, we're going to take a look at 3.2 numbers 29, 31, 32, 34, and 39, and section 3.3 numbers 4 and 14. So starting with number 29, compute det b to the fourth when b is the matrix 1, 0, 1, 1, 1, 2, and 1, 2, 1. All right, so the theorem that we want to use here is that b to the fourth, of course, can be thought of as 4 copies of b multiplied. And we had a theorem that told us that the determinant of a product equals the product of the determinants. So this is really det b times det b 4 times. So we have to compute det b, which I'm going to do by cofactor expansion along the first row. So that's 1 times 1, 2, 2, 1, plus 1 times 1, 1, 1, 2. So here we have 1 minus 4, and here we have 2 minus 1. So we've got negative 3 plus 1, which is negative 2. So our answer is negative 2 to the fourth, or 16. Okay, 31. Show that if A is invertible, then det A inverse equals 1 over det A. Okay, so let's start this by saying that A times A inverse equals I. And then let's take the determinant of both sides of this equation. So det A inverse equals det I. If it's not intuitive, det I is 1 because it's a triangular matrix and all of the elements on the main diagonal are 1, so we can multiply all those. And on the left side, we can use our theorem that says, same as before, the determinant of a product is the product of the determinants. So this is det A times det A inverse equals 1. And the thing we're trying to prove is that det A inverse is 1 over det A. So we're basically there. Divide both sides by det A and we have it. Det A inverse equals 1 over det A. Okay, moving on to 32. Suppose that A is a square matrix such that det A to the third equals 0. Explain why A cannot be invertible. Okay, we're going to use the same reasoning as we did in 29. Det A to the third is going to be the same as det A to the third. And by zero product property, this implies that det A must equal 0, or rather just solve that equation. If det A equals 0, we know from the IMT that A is not invertible. And that's our most recent addition to that theorem, that when determinant equals 0, the matrix is not invertible. Okay, 34. Let A and P be square matrices with P invertible. Show that det PAP inverse equals det A. So this looks pretty random for us right now, but this is an important idea when we begin to diagonalize matrices with eigenvectors and eigenvalues. So it looks a little weird, but it's useful later on. So we're going to try and show this by starting with the same theorem as before. Det P times det A times det P inverse. Then we'll rearrange terms so that we can write this as det P inverse times det A. And det P inverse is the same as det I, since P is invertible. Det I is 1, and so we end up with det A, and we've proved it. And then the last problem is 39. There's 5 sections to this. Okay, so let A and B be 3 by 3 matrices with det A equal to negative 3 and det B equal to 4. So this is just applying the theorems from the section. So det AB is going to be the determinant of each of them multiplied. So A is negative 12. B is the determinant of 5A. Okay, so remember how this works. That means that every row is being multiplied by 5, which means the determinant will be multiplied by 5 3 times. So this should be negative 3 times 5 to the third, which is negative 3 times 125, which is negative 375. C, determinant of B inverse. It's the same as the determinant of B, so the answer is 4. D, determinant of A inverse is 1 over the determinant of A. So that's negative 1/3. And then E, determinant of A to the third is just the determinant of A times itself 3 times. So that would be negative 3 to the third, or negative 27. All right, that's it for section 3.2. Let's look at 3.3. So we'll start with number 4, which is a Cramer's rule problem. Okay, so number 4. The system is negative 5x1 plus 2x2 equals 9, and 3x1 minus x2 equals negative 4. So matrix A is negative 5, 2, 3, negative 1. A sub 1 of B, remember what this means, we're putting B in place of the first column of A, so it would be 9, negative 4, 2, negative 1. And then A sub 2 of B, we put B into the second column of A. So negative 5, 3 remains as the first column, and then 9, negative 4. Let's find the determinant of each of these matrices. So first determinant would be 5 minus 6, or negative 1. Second determinant would be negative 9 plus 8, so also negative 1. And the third determinant is 20 minus 27, so negative 7. So x1 is negative 1 over negative 1, so x1 is 1. And x2 is negative 7 over negative 1, so x2 is 7. And let me just confirm that with the solutions that I'm actually right. X1 is 1 and x2 is 7. Good. Okay, and then the last question is 14. This is the one you're probably least prepared to do based on how far we got in the lesson, but we'll give it a try. So it says compute the adjugate of the given matrix and then use theorem 8 to give the inverse of the matrix. Okay, so this is going to be a little bit of work. Here's the matrix. All right. The adjugate requires us to compute each of the cofactors. So I'm going to list them all out, and then we will compute together. Okay, so actually, I did this accidentally, but I put these in the order that they will appear in the adjugate. So we'll be able to just take these numbers and make a matrix out of them, and that'll be the adjugate. So C11, remember, is negative 1 to the 2, so that means we can ignore that part. And it's the determinant of the minor that's formed when you delete the first row in the first column. So it's really the determinant of 2, 1, 0, 4, which is 8. C21, delete the second row in the first column, plus a negative in front, right? So negative 1 times second row, first column, we got negative 1, 2, 0, 4. So our determinant, or our cofactor here, the determinant is negative 4, the cofactor is 4. C31, delete the third row in the first column. We don't need to worry about the sign here. Negative 1, 2, 2, 1. So I have negative 1 minus 4, or negative 5. C12, delete the first row in the second column and have a negative out in front, so that's important to remember. So first row, second column, 0, 1, 2, 4. So our determinant is 0 minus 2, so negative 2 times negative 1 gives us 2. C22, don't worry about the sign. We've got 1, 2, 2, 4. So it's 4 minus 4, which is 0. C32, delete the third row and the second column. Third row, second column. So we've got a negative out in front. And we've got 1, 2, 0, 1. That gives us negative 1. Delete first row, third column. Don't worry about the sign. 0, 2, 2, 0. The determinant is negative 4. Oh, sign out in front's got to be negative on this one. Second row, third column. Second row, third column. 1, negative 1, 2, 0. So that's 0 minus negative 2, 0 plus 2, but there's a negative, so negative 2. And then C33, don't worry about the sign. 1, negative 1, 0, 2, so we've just got 2. Okay, so the adjugate of A, this is the result of all that work, is 8, 4, negative 5, 2, 0, negative 1, negative 4, negative 2, 2. Let's confirm that's right before we go on. Okay, adjugate is 8, 4, negative 5, 2, 0, negative 1, negative 4, negative 2, 2. Perfect. Okay, great. This means that using our theorem 8, let's go back and look at that. Theorem 8 says that A inverse equals 1 over det A times the adjugate of A. But we don't want to compute the determinant by hand. That's a pain. So instead, we're going to use the formula that says that det A times I is equal to the adjugate of A times A. Here's where I'm going to use a calculator. Now, I know the whole thing could be done quickly on a calculator, but I just want to do this multiplication quickly. So we're going to take the adjugate of A times A on the calculator. Okay, here's the adjugate of A. 8, 4, negative 5, 2, 0, negative 1, negative 4, negative 2, and 2. We're going to multiply that by matrix A. Matrix A is, just a second, sorry, 1, negative 1, 2, 0, 2, 1, 2, 0, 4. Now what we're going to reveal here is the identity multiplied by whatever the determinant is. Cool, so that means the determinant is negative 2. So we kind of use this little cheater step to get the determinant. Determinant of A equals negative 2. So our theorem tells us we can just take 1 over negative 2 times the adjugate to get A inverse. All right, so let's clean this up. We'd have negative 4, negative 2, 5 halves. And then we have negative 1, 0, 1 half, 2, 1, and negative 1. And we're done. That's the inverse. So how does that compare to having to ref augmented with the identity? I don't know. Of course, the best method overall would be making the calculator find the inverse. All right, we can answer more questions in class. Thanks for watching.